Okay, so we had in the morning introduced this field. Which transforms like this under the SU3 cross SU3 symmetry, and we saw that the Lagrangian at order p squared was f squared over 4 trace d mu sigma dagger. Now, okay, so this is called the order p squared Lagrangian. Then at order p to the 4th, and I should remind you, we're setting quark masses to 0. We'll come back and put in the quark masses. So at order p to the 4th for SUNF, chiral perturbation theory, the standard, so you write down all the possible terms, make sure you use the integration by parts and feed redefinitions and everything. And what's left are these coefficients, the L coefficients with hats on them. I guess I keep mixing my notation. Okay, angle brackets for trace, d mu sigma dagger, d mu sigma squared, plus L2 hat, d mu sigma dagger, d mu sigma dagger, d mu sigma, plus L3 hat, d mu sigma dagger, d mu sigma dagger, d mu sigma. And then, okay, so you might have thought this was L4, but it's called L0. D mu sigma dagger, d mu sigma dagger, d mu sigma. And, okay, so there's only 4 terms. If you include masses and external sources, which if I have time I'll discuss, then there are like 15 coefficients or something at order p to the 4th. Now you can see that we saw that sigma was e to the 2I pi. I'll also use just capital pi to stand for TA pi a. I'm not supposed to write this high, but you can see that when you do d mu sigma, every d mu sigma at least has 1 pion in it to get a derivative. So all of these terms start at 4 pions and have 4, so they're like d pi to the 4th plus more pions in them. Now, there's one subtlety here, which is the following, that when you do these matrix traces, there's something called the Cayley-Hamilton theorem or the Cayley-Hamilton identities. So if you take 2 by 2, okay, so for 2 by 2 matrices, 1/6 the trace of A whole cubed minus a half trace of A squared plus 1/3 the trace of A cubed is 0. There's just an identity for any 2 by 2 matrix, and you can verify it. You know, if you have Mathematica, just write down a arbitrary 2 by 2 matrix and check this. Now, if okay, so this is step 1. So for an NF by NF matrix, there will be an identity which allows you to write the trace of A to the NF plus 1 in terms of lower powers. Okay, so here the trace of A cubed could be written as lower order traces. These 2 terms only involve trace of A and trace of A squared. So any trace of A cubed or higher can be removed in terms of these. And this, any matrix, yeah, but 2 by 2. And I'm mentioning this because this identity depends on the size of the matrix. Yeah. Okay, so see if you can figure out how to prove that. If I then vary this identity with respect to A, they take the first derivative, then what you find is that A squared minus A trace of A minus a half, let's see, the trace of A squared times the unit matrix plus a half trace of A squared times the unit matrix is equal to 0. So now you get a one lower order identity by differentiating that with respect to A. And then what you do, so now this thing started with cubic terms, so this one has quadratic terms. And then what you do is you let A go to A plus B and pick out the terms which are A times B. So this mathematicians call this taking the polarization of this formula. But what it tells you is that AB plus BA minus A trace of B minus B trace of A minus AB trace of 1 plus trace A trace B times 1 is equal to 0. Okay, and this is true for any two 2x2 matrices A and B, just an identity. So for 3x3 matrices, there's a similar set of rules you can work out. I won't write them down. Yeah. Eigenvalue equation, and from that you can get this. So it's related to that. So that's basically the second form. And yeah, so that's why it's called it's coming from that. And then what you do is you take the matrix and replace it by A plus B and pick out the AB terms. And okay, so there's a similar identity for the case of 3x3 matrices. It's going to have more terms because here the identity will involve A through to 3, etc. Now, when people talk about SU-NF chiral perturbation theory and write down this Lagrangian, if NF, you don't know what NF is, you can't use any of these identities because the identity depends on NF. So this is like the general structure. So then you can go to SU3 chiral perturbation theory, where NF is 3. And you use the 3x3 version of this identity, which I haven't written down. You can look in this Bainen's, Colangelo, Ecker paper. But if you do that, then these 4 terms are not independent. And basically you can rewrite L0 as some combination of these. So the perturbation coefficients for SU3 are called L's but without a hat. And L1 is L0 hat over 2 plus L1 hat. L2 is L0 hat plus L2, and L3 is minus 2 L0 hat plus L3 hat. So basically the terms look exactly like this, except that the coefficients are called L1, L2, L3, and maybe just to be on the safe side, we can say that L0 is 0, that is, you're dropping the L0 term. And what the identity has told you is that the L0 term is 1/2 the L1 term plus the L2 term minus 2 times the L3 term. That's the Cayley-Hamilton identity for flavors. So you'll see sometimes people talk about L hats, that's this form, or you do, for SU3, you throw this away and then you have to reshift because of this linear relation. Then you can do SU2 chiral perturbation theory, where NF is 2, where you use this n equals 2 identity, and then it turns out there are only 2 coefficients, which are historically the Gasser-Leutwiler coefficients, which are called little l, and that's minus 2L0 hat plus 4L1 hat plus 2L3 hat, and L2, which is 4L0 hat plus L2 hat. So the standard convention is the hats are for NF, the capital L's are for SU3, the lowercase l's are for SU2, and unfortunately the normalization is, the Lagrangian is little L1 over 4 trace d mu sigma dagger squared plus L2 over 4 d mu sigma dagger d mu sigma, sorry, d mu sigma dagger d mu sigma. So for some reason, not some reason, I mean, the original Gassel-Leutwiler paper did SU2 chiral perturbation theory, and they used little l's, and they didn't use the sigma field. They used a slightly different notation, which ends up producing a relative factor of 4. So really, these maybe should be the SU2Ls, but okay. If you look at the literature, it's always in terms of these little l's, and so that's where the 4 comes from. It's basically their chiral field was 1/2 the sigma field, which is why you're getting a 4. The way they normalize things. Okay. Now we can. Okay. So any questions on this? So this is the P4th Lagrangian. People have. I think they have now done the P to the F. Well, certainly the P6 Lagrangian was done a long time ago, and I think the P8 Lagrangian, all the terms have been worked out. It's a highly non-trivial exercise to count how many terms. Maybe there'll be a talk next week on this. How to count how many independent terms there are using the integration by parts and field redefinition identities. Okay, so this is the Lagrangian we have. Okay, so we have some, and I'll do the power counting. So there's L2 plus L4 and L6 and L8 and so on, just like in the SMAFT or one of these other EFTs. Okay, so we can already do something. So the transformation we had, the SU3 left transformation, Q left went to e to the I epsilon left A TA times Q left. And if I take the QCD, okay, so I want to calculate the symmetry currents corresponding to these transformations. And this is a global transformation, and the way you calculate the symmetry current is you make the same change of variables, this one, but you make epsilon a function of x. If I take the QCD Lagrangian, the relevant term is this, the kinetic term for the left-handed quarks. And when I make this transformation, this is a unitary transformation. It would cancel because you would get the transformation here and the Hermitian conjugate on the other side. But if epsilon depends on x, there's an extra term where the derivative acts on the epsilon, which wasn't there in the global case. So in the global case, we would have put an L here and an L dagger, and everything would have canceled. But if L depends on x now, there's a piece where the derivative acts on the transformation, and this gives you, okay, so there's an I in here and an I in there, and if I work to first order, I get minus d mu epsilon A, q bar left, gamma mu, T A Q. And this is Noether's theorem, basically, and this tells you what the left-handed current is. You get it by applying an infinitesimal symmetry transformation, and the coefficient of minus d mu epsilon is the current. So that's one way to get the symmetry currents. And the right-handed currents given by parity, you basically just replace Q left by Q right, and those are the right-handed currents. Now in the EFT, the Lagrangian was f squared over 4, the trace of d mu sigma dagger, d mu sigma. And by definition, my EFT is implementing the symmetries of the full theory, so I can calculate the symmetry current corresponding to this quark symmetry current in the EFT by making the same symmetry transformation in the EFT. So sigma, somewhere over there, sigma goes to L sigma R dagger. I'm just making a left-handed transformation. So sigma goes to e to the I epsilon LA TA. Sigma. So if I now look at what's happening, Maybe I should just write it, it's maybe easier to just write this as L sigma. Then L effective goes to F squared over 4, the trace of d mu sigma dagger L dagger d mu L sigma. And so the change in the Lagrangian is F squared over 4. And you get a piece from here, which is d mu sigma dagger. And the derivative acting on L dagger to first order is minus I d mu epsilon LA TA. And then I have here d mu sigma. And the other term is d mu sigma dagger d mu L, which is I. Wait, something's wrong. Yeah, so the d mu here is acting on the L dagger, so there's no d mu on the sigma dagger. The d mu acts on the L. And here there's an I d mu epsilon LA TA, and the derivative is acting on the L, so I just have a sigma. So overall, I get I F squared over 4 d mu epsilon A times the trace of minus sigma dagger TA d mu sigma minus, yes, plus d mu sigma dagger TA sigma. Wait a second. Oh, I did the right-handed currents. Okay, so the left-handed currents are minus TA. Okay, anyway, let's see if I got this right. And now you can simplify this term because here the d mu acts on the sigma dagger, and there I'm sorry, on sigma, and there the thing acts on sigma dagger, but I know that sigma dagger is 1. So d mu sigma dagger, just differentiating, plus sigma d mu sigma dagger is 0. So taking this to the other side and multiplying, you can see that d mu sigma dagger is minus sigma dagger d mu sigma dagger. So if I write both of these terms with the TA at the beginning, I can see that J mu LA, which is, okay, the coefficient of d mu L epsilon L is minus the current. So it's IF squared over 4 times the trace, and I have to flip the sign. So this is TA d mu sigma dagger. And then from the second term, again flipping the signs, I get minus, this term is sigma dagger d mu sigma dagger TA sigma. And here, because this is inside a trace, the first term, and I can move this last term to the beginning and cancel the sigma with the sigma dagger. And again, because it's inside the trace, I can put the TA first, and then I get TA d mu sigma dagger, which is the same as that. And I should have had a, oh yeah, so this is plus, that's minus, because I flipped the sign, and then there's an extra minus sign from this identity, so they both, it just doubles this. And you get I F squared over 2, the trace of TA d mu sigma dagger. Yeah, okay, so this is right. So this is the left-handed current, and the right-handed current is given by the parity transform. So that's given by I F squared over 2, and parity means pi goes to minus pi, or sigma goes to minus sigma. So this is TA, d mu sigma dagger, sigma. So we have the currents corresponding to the QCD currents, the flavor symmetry currents of QCD, which are here. We have the same operators in the chiral Lagrangian, because the one thing that the EFT knows about are the symmetries of the original theory, so you can calculate the symmetry currents. Okay, so any questions on this? Just applying Noether's theorem to QCD and then Noether's theorem to the EFT and equating. So this operator, Q bar, this operator in QCD maps on to this operator in the EFT. And if I work it out, so now you just expand, sigma is the exponential of pions. We've been doing this again. You just expand it out as 1 plus pi squared, etc. Then you find the J mu right A is F over 2 d mu pi A plus a half F A B C pi B d mu pi C plus dot dot dot. Because you get a commutator of 2 pions, which gives you the structure constant, and the left-handed current is given by flipping the sign of the pion because of parity. Pi B d mu pi C plus dot dot dot. So we can calculate the vector current. The vector current is simply the sum of the left and right-handed currents. And because pi is going to minus pi, when you add the two, all the odd powers of pions cancel. And you get FABC pi B d mu pi C plus even pions, so 4 pions, 6 pions, etc. And the axial current, which is the right-handed minus the left-handed current, is F d mu pi A plus odd powers of pions. And okay, so now here you can see that the broken symmetry current, the axial current, has a term linear in pions. And from this you find that the matrix element of the axial vector current between a 1 pion state, a type B pion, let's say, with momentum P is minus IF P mu delta AB. Okay, because a derivative on an incoming field gives you minus I momentum on that field. And if you have a pi B, this index A had better be B so that you can annihilate it. And F, which is about 93 MeV, we'll see why in a second, is called the pion decay constant. And it's a measure of the strength of the symmetry breaking, just like the VEV was a measure of the strength of the symmetry breaking in the ON model. Okay, so the old PCAC results from the 1960s, where nobody knew about QCD or anything, just assume there was this matrix element with an F pi, and then you can go calculate. Okay, so any questions on this? Okay, so now we can go do pion decay. Pi minus by the weak interactions to L minus nu, nu bar. Okay, so L here is either the electron or the muon, which are the 2 leptons lighter than the pion. And we already saw that the Fermi, the low energy, because the momentum transfers in this process are afforded the pion mass, which is like, for the charged pions, like 139 MeV, is much smaller than the weak scale. We can use the effective weak Hamiltonian, or weak interaction Lagrangian, which is U bar gamma mu P left D L bar gamma mu P left nu L. So that's my interaction Hamiltonian, or interaction Lagrangian. I'm working to first order in the weak interactions. So what I want to calculate is pion coming in, decaying. I think I did P1 here. This is a lepton. P2 going in. This is the antineutrino of the lepton. Sorry, so P2, sorry, the fermion arrow is going this way, the momentum is flowing that way. Here the momentum and the arrow are both flowing the same way. So pi minus decays to mu minus mu bar, E minus mu E bar. We can do both of these at the same time by just calling the lepton L. Okay, so what's the matrix element for this? The amplitude is given by, if this is a term in the Lagrangian, you get a factor of I when you expand out the operator, just from the fact that it's e to the I action. So you get minus I 4G Fermi over root 2 VUD. The leptonic part is trivial. You just put the spinners on because so the Feynman rule is U bar of P1 gamma mu P left V of P2. And then what we need is the matrix element. You're starting with a pion, and as far as the strong interactions are concerned, what's happening here is you're ending up in the vacuum because the leptons don't count as far as QCD is concerned. So you have the matrix element between the vacuum U bar gamma mu P left T, pi minus of momentum P. I called it P pi, okay. So that's the matrix element I want, or pi decay. Okay, is this clear? Yeah, so P pi will be P1 plus P2 because it's decaying into those two. Yeah, so momentum conservation. That's this one, yeah. Well, that's the momentum of the pion, so that's the physical matrix element you want, but yeah, momentum conservation means that it has to be P1 plus P2. No, that in any frame, right? Momentum conservation is true in any frame, so this is true in any frame. But I will eventually calculate it in the rest frame. Okay. Now, this is a left-handed current. We just went and calculated the matrix element of the left-handed current. It's minus IF d mu pi. Now, so this would be minus I. Sorry, the derivative brings down I minus I pi, so this is I f over 2 p pi mu, except that these currents were normalized so that my states pi A, etc. were pi 1, pi 2, pi 3. And here, the pi minus is like pi 1 minus I pi 2 over the square root of 2. But this current is like the T1 current plus or minus I times the T2 current without a square root of 2. So you get an extra factor of square root of 2 here just from the normalization. If I'd put a root 2 here, then this would be normalized like the pi minus, and I would have gotten an f pi, but I don't have this root 2, so I get an extra square root of 2. Okay, because this is like a, I don't know, raising or lowering operator, whatever. It's like T1 plus or minus I T2, but to normalize things like the pion, I should have had a root 2 there. So there's an extra root 2. Oops. So, well, I'll have to, let me stay on this side of the board. Okay. So what is the amplitude? Okay, the I and the minus I cancel. So I get the root 2 and the 1 over root 2 cancel and the 4 over 2. So you had 2G Fermi VUD, the pion decay constant. P pi mu, which I'll now write as P1 plus P2 mu, U bar of P1, gamma mu V of P2. So that's the amplitude. Okay, so you can see that using this, we actually have the weak interactions are like some external current, a weak current, and I've calculated the matrix element of the weak current in a hadronic state using chiral perturbation theory. That's what I've done. Because here, what I need from the strong interactions is this matrix element, a current, and the currents I know how to do because those are related to symmetries. Now, if I look at this, I get U bar of P1, P1, I'm sorry, there's a P left here, did I? P1 slash P left V of P2 plus U bar of P1, P2 slash P left V of P2. Now I can pull the P, I can put the PL here and make it a P right, because when the gamma 5 anti-commutes, but P2 slash on V of P2, well, the neutrino is massless, and the Dirac equation tells me that P2 slash on V is 0. So this term's 0, neglecting neutrino masses. On this side, I can act with the P1 slash on the U of P1, and that gives me the mass of the lepton, U bar P1, P left V of P2. So we know that the amplitude is proportional to the lepton mass, and the reason for that is, suppose I have a pion sitting here, which now decays. So the lepton goes this way, the antineutrino goes this way. Now the weak interactions couple to left-handed fermions, so the lepton is left-handed, so its spin points this way. The neutrino is left-handed, so the antineutrino is right-handed, so its spin points this way. And this violates angular momentum because the pion has 0 spin, and if I look at angular momentum along this axis, you get 1 unit of angular momentum. But luckily, chirality and helicity are not the same thing. If I look at a left-handed fermion, it has a little piece of a right-handed particle in it, and people denote that by putting a helicity flip here, which is proportional to the mass of the lepton, and it flips the helicity of the electron to the opposite one, and now you add up with angular momentum 0. So that explains why there's an ML here. Okay, now you can, okay, I have it in my notes, but I'm not going to waste time on this now. So now you take the amplitude squared summed on spins, which from here is going to basically give me a trace of P1 slash plus ML, P left, P2 slash P right. You calculate the trace, put in the two-body phase space, and okay, so this is another calculation you should check. You get gamma. So gamma pi minus to L minus mu L bar is G Fermi squared over 4 pi F squared VUD squared M pi ML squared. Okay, so we can already see, I mean, the G Fermi squared VUD squared F squared is coming from here. There's an explicit ML, which is giving the ML squared. And then two-body phase space has like a 1 over 8 pi or 16 pi or whatever. So that's this. And then everything is governed by M pi, and you get 1 minus ML squared over M pi squared. So that's what you get for the decay rate. Okay. Yeah. You just have to do these traces, and you'll get like P1 dot P2 and yeah, because P1 dot P2, I mean, so for example, P1 dot P2 will be, so 2 P1 dot P2 would be P1 plus P2 squared minus P1 squared minus P2 squared. And P1 plus P2 squared is m pi squared. P1 squared is ml squared, and that's the neutrino is 0. So now you factor out an m pi and you get, so you just have to do the phase space. I mean, the phase space is governed by m pi and ml. So it's coming from the phase space and this trace. So that's also where this another second factor here comes in. Okay, so now this is a famous calculation. This is using current algebra basically to calculate the, a weak, you're using physics of strong interactions to go calculate a weak decay rate. And now you'd go to the, okay, so here's another exercise. Go to the PDG, look up the pion lifetime into mu minus. You know the value of G Fermi, VUD, all of these things, you can get F. And this gives me F is about 93, I think 0.06 or something MeV. So this is where you get the pion decay constant as about that. And okay, so there's another experimentally important quantity here, which is you can calculate the rate of pi minus to E mu E bar over pi minus to mu minus mu bar, right? Where all of this stuff drops out and you're just left with this kinematic thing. So it's me over m mu whole squared, 1 minus me squared over m pi squared divided by 1 minus m mu squared over m pi squared. And so this is much, much less than 1 because the electron is 200 times lighter than the muon, so you're getting like 1 over 40,000 or whatever. So if you look in the particle data book, you'll see that the pi minus decays almost 100% of the time, 99.97% into muons. And this is why. And it's relevant for experiments because their pion can produce muons or in cosmic rays, but not electrons. Okay, so here's one example of using Chiral. Well, we haven't really succeeded in doing anything because we didn't know what F was, but at least this now tells me what F is. But I could, in principle, do things like pi plus to pi 0 E nu, that there's not enough energy for the muon. And now I could have expanded the left-handed current to second order in pion, and I can calculate this now with no free parameters. But that's more complicated because there's 3-body phase space and so on. But this is the kind of thing people do. Or you can do k decays, for example, and k to pi pi and k to 3 pi and so on are all related. And the parameter you need is F. Okay. So any questions on this? Well, they're the same at this point. Yeah, so that's right. So then when you start doing Chiral corrections, then, okay, I don't know what so the F that people use is the F which enters in the Chiral Lagrangian there. And I mean, this is now a question of what the words are. So when you calculate the matrix element of the current with the pion, we have a diagram which looks like this. But there's also a 3 pion amplitude like that. And if you do the 1 pion matrix element, you can get a loop like this. And now, so these are, yeah. So I don't, as far as I'm concerned, I would just put F as the F in the Lagrangian, and then you can call this something, whatever you want. And this will be different for the pion and the kaon and so on, because these loops will be 0 unless the pion has a mass, but if there's a mass, this will go like some m pi squared log m pi squared over mu squared correction. Something like this. And this will break all the SU3 symmetries, so the correction for kaons and pions and etas will be different and so on. I don't remember whether they call them, so these are the physical decay constants. They were doing this because this is what comes into the experimental decay rate. That's right. And then we're comparing with chiral perturbation theory, the lowest order, and we're going to put in the mass. And then if you put in the mass, you can do the next order correction. So what we're doing would be like order, I don't know what you want to call it, order 1, and this would be like the p squared correction, and people have done the p4th correction as well. Yeah. No. There is no scale dependence in F. So even in we'll do Weinberg's power counting, which I'm doing next, and you'll see F does not have a mu dependence in MS bar, for example. It's fixed. And another way to see this is where is it going? I erased it, but this is the matrix element of a current which has no anomalous dimension. And so the F can't have an anomalous dimension. So F is 93 MeV, and it's mu independent. Okay, well, let's do this next thing, and then maybe it'll become clearer. Okay, other questions? Okay. Okay, so yeah, so now you have to put together multiple experiments. So people look at processes where the matrix, like nuclei, where the matrix, hadronic matrix element is known from some symmetry. Actually, you could do, where's it gone? The pi plus to pi 0 you knew, where you get a vector current comes in, and the vector part of the left-handed current comes in, and this is normalized because of isospin, and then you can determine VUD. So there's a whole PDG note on CKM matrix elements, and you can look. So yeah, there's a lot of calculations in physics and things which go into like determining all of these parameters. Like how do you determine G Fermi and everything else, yeah. So you have to calculate a process where the hadronic matrix element has no parameter in it so that you can then get VUD. Yeah, so it's some nuclear, there's some 0 plus to 0 plus nuclear transition where these things form some isospin multiplet. So J mu left is U bar gamma mu P left D, so that's U bar gamma mu D minus U bar gamma mu gamma 5 D over 2. So you calculate a process where this current enters because of the parity of the states. So for example, pi plus to pi 0, both are negative parity, the vector current will contribute, not the axial current. Now this is an isospin raising operator, so the matrix element between pi 0 and pi plus will be square root of 2, not F pi. Did I erase my current? Yeah, I erased the current, but the first term was F d mu pi, but the second term, which was the structure constant pi d pi, has actually no F in there, no pion decay constant, just a structure constant. So it's completely normalized. So then you use that matrix element, and so the matrix element's known, and then there's just an unknown, which is VUD, and then you can measure VUD that way. There's lots of, yeah, there's a whole, I mean, now you can, there's an endless amount of stuff you can do. I mean, you can also compare leptonic weak processes which don't have a CKM matrix element to the corresponding hadronic one, and then the ratio G Fermi cancels out and the VUD will stay, things like this. Okay, so the thing I wanted to get to was Weinberg's power counting argument for chiral perturbation theory, which will make some of the stuff clearer. So we see here Okay, there are 2 derivative terms, 4 derivative terms, 6 derivative terms, and so on, and you expand everything in powers of, the sigmas are really just a shorthand for exponentials of pions. So I'm going to write my Lagrangian as a sum k bigger than or equal to 2 of L sub k, where L sub k means terms of order p to the k. And we saw that the smallest k could be was 2. There is no term with no derivative. So the first term, the d mu sigma dagger term, started off at order p squared. And now take some random diagram, okay, some arbitrary diagram like this, a generic loop graph, and work out with arbitrary vertices from any of these things, and let's work out what the amplitude looks like. So the amplitude goes like the integral d4p over 2, well, the 2 pi to the 4 doesn't matter here. So there's some generic integral d4p for each loop. So you get some integral like this to the order of, power of the number of loops. Every internal pion propagator is a 1 over p squared. The propagators go like 1 over some momentum squared. So you get some 1 over p squared to the number of internal lines. And then every vertex here has some power of p. So if the vertex comes from the L2, the d mu sigma dagger term, it has 2 derivatives in it. If it comes from L4, it has 4 derivatives, etc. So you get the product over k of p to the k, v to the k. So this is the number of vertices which you have from Lk. So V2 would be the number of vertices you have from the L2 Lagrangian, V4 would be the number of vertices from the L4 Lagrangian, etc. And the L2 Lagrangian has p squared, the L4 Lagrangian has p to the 4th. So this is like the factors, all the factors of p from all the vertices multiplied together. Is this clear? Okay, so loops, propagators, vertices, just counting momentum factors. For a fixed diagram. No, but that's what k means. So this symbol just means L2 plus L4 plus L6. So V2 is V2 is the number of vertices from L2, and V4 is the number of vertices from L4. So this vertex could be from L2, this vertex could be from L4, that vertex could be from L6, this vertex could be from L2. Okay, let's just keep going. This could be from L4, this could be from L6. So in this diagram, V2 is 1, 2, V4 is whatever, 1, everything is 2 in this. Okay, V4 is 2, and V6 is 2, because there are 2 vertices from L2, 2 from L4, and 2 from L6. And each of these vertices produces p squared. So here I get, let's just make this L4 as well. So now you have 1, 2, 3 L4s and 1 L6, okay. So then each of these vertices produces, there's a p squared at this vertex, there's a p squared at this vertex, there's a p fourth at this vertex, etc. So this gives me p squared squared, p fourth cubed, p6 times 1. That's this factor. Just try writing down an example and just seeing what happens. So this whole integral gives me something which is of order p to the d, some factor of momentum. And okay, the key thing which we're all using in our lectures is when you have dimensional regularization, you only get the scales which are there in the problem. You never get factors of mu anywhere. And P here is some generic momentum, some external momentum of some kind, because the loop in momenta are integrated over. And so you can read off what D is. D from here is 4 times the number of loops. Then this is in the denominator minus twice the number of internal lines. And from here, you get the sum on K of K VK. So that's the power of, it's manifest power. It's called manifest power counting. You just count the powers and that's the result. Because there's no way to replace powers of P by something else. Okay, is this clear? And now you want to get rid of this I here. And there's a topological identity for connected Feynman graphs, which is vertices minus internal lines plus loops is equal to 1. So multiply this whole identity. Okay, so let's write it this way. Minus 1 is equal to 0. So multiply this whole thing by 2. So I get 2v minus 2i plus 2l minus 2 is equal to 0. And subtract. So I get d. So 4l minus 2l is 2l. The 2 i's cancel. I get a plus 2 from here. And I get plus the sum on k, k vk, minus 2v. And so I'm going to take the 2 to the other side and write d minus 2 is 2l plus the sum on k. And now what is v? V is the total number of vertices. And I'm saying v sub k is the vertices from L sub k. So the total number of vertices is simply the sum on k of v sub k, because it's the sum of the vertices from L2 plus L4 plus whatever. So I can combine these two terms and write this as k minus 2 vk, sum on k bigger than or equal to 2. So this is the famous, this is Weinberg's formula. It's sort of the first power counting formula in an EFT, I think. So why is this? Anyway, so before I go on, okay, so is this clear, the derivation of this? It's pretty straightforward. And all of these formulae require this what topological identity on connected graphs. Okay, now on the right-hand side, because my Lagrangian starts at power k to the 2, I have the inequality that k must be bigger than or equal to 2. There are no terms with 0 or 1 derivative. K is bigger than or equal to 2, which means k minus 2 is bigger than or equal to 0. And the number of loops, you can have tree level, but you can't have -1 loops. So the number of loops is bigger than or equal to 0. So both terms on the right-hand side are at least 0 or bigger. That tells you that the loops can only generate diagrams with d bigger than or equal to 2. So you cannot generate a L1 term or an L0 term or whatever, the p to the 0 or p to the 1. You at least generate p squared. Okay? So you always move one way. You can only increase the degree of the powers of p. You can't decrease them, essentially, because everything here is positive. Now, what is the smallest you can go? So you can get d equals 2. For d to be 2, both of these terms have to be 0. So L is 0 means tree graphs. This being 0 means the only vertices you can have to have k equals 2, because otherwise you get something positive. So this is tree graphs from L2. Okay, now the next D I can do is 4. So I can get 4 by having one loop that already saturates the 4 here, because 4 minus 2 is 2. I need to produce a 2. So L equals, so loop graphs, sorry, one loop graph from L2. Or this term's gone and I have to get a 2 from this term. The way I get a term 2 from this term is I have some insertion of V4, some insertion of, but I only have to have one of those because that produces a 2 here. So, or tree graph with one L4 vertex and any number of L2 vertices. Let's just say from any number of L2 and any number. Basically, you can always add any number of L2 vertices and it not mess up anything because it contributes 0 to this side. Okay, now you want D equals 6. Well, you can have 2 loop graphs from L2, or you can have a 1 loop graph. So with one L4, or you can have a tree graph, and the tree graph can have 2 L4s or 1 L6. Hopefully I did this right. Okay, and you can keep going, but you can see what the structure. So one important thing here is that if you start with the p-squared Lagrangian and you do one loop diagrams, you generate, okay, so with L2, one loop produces L4, 2 loops produces L6. Basically, every time you have a loop, you're increasing the divergence by 2 at least. I mean, well, exactly 2 for each loop. So if you think of this as L2, L4, L6, etc., then a loop, one loop, each loop takes you from here to here, here to there, etc. You're moving up in dimension just because of the 2L. Now, loop graphs can be infinite, and you end up with RG flows. But here what's happening is that a one loop graph with an insertion of L2 gives me mu dd mu of L4 is proportional to the L2 coefficients. But there aren't any L2 coefficients. It's basically F pi. So the running of these L hats, what I call, everything is L, but okay. These coefficients L hat I in the chiral Lagrangian, they do depend on mu. Mu dd mu of these L hats is just some numbers with some powers of F pi. Because they're coming from one loops with the L2 Lagrangian, etc. So you can see F pi doesn't run because F pi is in the L2 Lagrangian, but any loop graphs run the L4 Lagrangian. There is no running of the L2 Lagrangian. Because the one loop at least shifts you to L4. So that's why F pi doesn't run, and then, so this is very different from like SMEFT or QCD or something where the Lagrangian can renormalize itself and the couplings run. Here, the running of the L6 Lagrangian is proportional to the L2 coefficients from 2 loops and the running of L4, etc. And so you move in this chain. So if you're at some order, L6, it doesn't run proportional to L6. It only runs proportional to things at lower order in P because the 2L factor there increases the dimension, the peak power counting by 2 units. Okay, so this is explaining the structure of the theory, and then we can do a few more things with that. But this is like a famous power counting formula. So when people work out chiral perturbation theory to order p to the 6, they're doing 2 loop graphs from L2, they're doing this, 2 loop graphs from L2 and 1 loop graphs from L4. And then if you're just doing the renormalization, that's all you need to calculate because 3 graphs are finite. But if you're calculating a cross-section or something, then you have to also include these tree graphs. We'll come back, yeah, okay, so there's a whole fight over what to do with E&M, but and also how to do quark masses in the counting. But yeah, so this is pure chiral theory, but once you understand that, then you treat everything else like a perturbation on top of this. Yeah, so what you can do is you can use large N QCD. And if you do large N QCD, if you will find that F pi goes like this, let me know, I'll just sketch it. F pi goes like the square root of N color. And the chiral Lagrangian, which is F squared over 4 trace d mu sigma dagger, is like N color times something. And then you'll see that in the functional integral, you get an e to the I N color over h bar times stuff. So the loop expansion becomes a 1 over N color expansion if you do large N QCD. But it's that sense in which you get you can organize things in the loop expansion if you introduce NC as an auxiliary parameter and put in the correct, well, okay, since you brought it up, yeah, put in the correct counting. So if you look at where these Lagrangian coefficients came from, these are what are called single trace operators. And single trace operators if you think of this as some sort of quark loop diagram, there's some flavor, and here's pion sticking around. And this loop means that you're doing a trace on flavor because whatever, this might become a U and a D and a whatever, but it has to come back to a U. So there's a trace in flavor. Now you can have double trace operators like this, where the mesons are somehow coupled here. And these are down by 1 over NC. And so in the, yeah, so so the single trace operator has got an NC there. And then the double trace operators have NC suppressions. And so L1 hat and L2 hat are double trace. And L3 hat and L0 hat are single trace. So these you would expect to be down by 1 over NC. And so you have to put that counting in, and then these are order NC, and then you can work it out, and you get this 1 over N expansion. So every loop will bring you 1 over N color. But you need to make sure your coefficients are consistent with the QCD large N power count, large N counting. But that's N flavor. And this is N color, which is different. Yeah, and the confusing thing is, yeah, you have 3 colors and 3 flavors, but okay, you just think of them as NC and NF, and yeah, so the NF is independent. NF fixed and NC large, yes. By 1 over what? No. Did you have a velocity? You're mixing theories or something. Oh, sure.
Yeah, 1 by.
But okay, but no. So let's just take one of these, right? So d mu sigma dagger, d mu sigma. Okay, anyway, that's a good question. So you do this, right? So now you get d pi over f to the 4th. Then you get d pi over f to the 4th, pi over f squared, and so on, right? Now, chiral invariance tells you that the operator has to have this form. This means that if you go do these diagrams and you calculate the running of this term, all of these have to run the same way, and you get some counter term, let's say, which is this operator. So if you calculate the running of this term, you can calculate the running of the entire operator. If you calculate the running of the second term, that's like a check, you will find exactly the same coefficient. And this is like in gauge theory where you have a covariant derivative, which is d plus IgA. And you normally don't check that the anomalous dimension of the d part and the a part is the same. You can check it, but that's a lot of work. So what people normally do is just work out this piece because it's easiest, and then use gauge invariance to say that the operator is a covariant derivative. So it's the same here. The chiral invariance tells you there's an infinite number of things, but they all renormalize the same. So that's why it's the running of this L hat coefficient. And that runs the whole thing as one object. It can't be, the different pieces don't run differently. And that's also why f pi cannot run, because it's e to the 2I pi over f. The time's up, right? Anyway, so we can just do questions if anybody has more questions. Yeah, every loop gives you a 1 over NC in the meson sector. Because basically where did it go? Yeah, it's because there's an NC in front of the whole Lagrangian, so the NC expansion is related to the 1 over NC expansion is related to the H bar expansion, which is the same as a loop expansion. So 2 loop diagrams will be 1 over n squared suppressed, 1 loop diagrams will be 1 over n suppressed, and so on. But you have to then put in the n, the fact that f pi goes like root n, and these l's, some of the l's scale differently with n than others, and so on. And okay, and one of the things you got to be careful about is if you use the Cayley-Hamilton theorem, which is true for certain NFs, and you're changing traces, you can mess up the NC counting. So it's best to use these L hats where no Cayley-Hamilton identity has been used, so that all the L's have some pure NC counting, and then every loop is a 1 over NC. That's correct, but it works very well actually, because I have done some. So with Elizabeth Jenkins, we had worked out baryon chiral perturbation theory and baryon mass relations and things working toward a 1 over n and doing some expansions. And if you do, if you can get identities which work to say, let's say 1 over n squared. So 1 over n squared is about a 10% effect, but you can get things which are higher orders in 1 over n, and you can get certain mass predictions which are correct to hadron masses to MeV or fractions of MeV. And in fact, one of the things which was done is some of the B baryon masses, B hadron state masses were predicted before they were measured, and they agreed to within 5 MeV of the experimental error, and whereas say the lattice predictions disagreed by 20 MeV or something. So but you have, that's a whole. I can maybe sketch it. Well, we'll see how many lectures, how far I get tomorrow, and then maybe on Friday I can discuss it. But I can give you some references. Yeah, so we worked out combining large N with chiral perturbation theory, and it's extremely helpful, especially in the baryon sector. So there's a whole series of papers from around 1995, before you were all born, but around 1995 or something like that, 94. So some of the mass predictions work extremely well. But you can't do everything, so you have to take certain linear combinations where the 1 over n's cancel and stuff like that. Wait, so what's happening is if you, so then you have like some d mu sigma, which is d mu sigma. So this is why I did not introduce sources at the beginning. Stuff like this, right?
Yeah, exactly.
Yeah, and then you're worrying about okay, so minus. I mean, there's just a contact piece, because here when you do this, right, you're going to get L mu sigma dagger L mu, which is a This is what you're worrying about, right? Yeah, it's just there.
Pure electronic squared is also
Yeah. It's just there by gauge invariance. And then you get some non-trivial stuff from here because you'll get L mu sigma R mu sigma dagger. You get stuff like this also. And then this is the stuff which produces the pi plus pi zero mass difference and stuff like that. Yeah. It's just there.
But you just live with it.
You just live with it. I mean, this is not separately gauge invariant, right? L squared is not gauge invariant. I mean, already if you're doing a scalar field theory, you get some phi dagger A squared phi term, right? It's sort of like that.
It says that phi doesn't have one.
Yeah, here, but phi dagger phi is 1. That's what's happening here. Yeah. It's, yeah, you just gotta keep it. And if you do the renormalization, this will have a counter term which will complete to give you, it'll end up becoming that.